Throughout the history of modern engineering, materials have forced compromises in design. The way a part can be created has always depended on the limits of the raw material itself. If you need strength, you usually choose metal. If you need lightweightness, then you choose plastic. But the moment you add heat or chemicals or steam or repeated stress, both of these options start to fail. For decades, engineers have been stuck living inside that trade-off, strength or lightweightness, with very little in between. But before we get into the story, it's worth saying why we care so deeply about this particular material. Here at Vision Miner, we've been 3D printing high-temperature polymers like PEEK for nearly a decade. It's our bread and butter. It's all we do. It's what our machines are built for, and it's what we work with every single day. This is the story of why engineers created PEEK, or Polyether Ether Ketone. Now, after World War II, engineering accelerated massively. Aerospace systems were being developed and they were getting hotter and faster. Chemical processing expanded rapidly as new industrial chemicals were introduced, and medical devices became more complex, and sterilization, both chemical gas and steam autoclaving, became standard. Now, across all of these industries, materials started hitting their limits. Metals were strong, but they were heavy, and they corroded under chemicals, and they fatigued over time and failed under cyclic loading. If you've ever bent an aluminum can tab back and forth a few times, you've seen this firsthand. Metal, not so strong with repeated stress. Now, engineering plastics were lightweight, but they would soften and they'd absorb moisture and they crept under load. If you hang a 20-pound weight on a plastic wall hook and then you come back a year later and that hook has been permanently deformed, that's creep. Many plastics simply dissolved or degraded when exposed to common industrial chemicals. So engineers weren't asking for better materials, they were asking for materials that could survive the new reality. The contradiction that nobody had solved was this. How do you make something that's strong like a metal, light like a plastic, and stable at high temperatures, chemically inert and resistant to steam, and able to survive years and years of cyclic stress? Most materials can handle one or two of those, but almost none can handle all of them at once. Heat alone eliminates most polymers. Chemicals eliminate most metals. Steam destroys dimensional stability, and fatigue will kill anything that isn't designed for it. By the 1960s and 70s, industries like aerospace, energy, and medicine were facing unacceptable failure rates. Incremental improvement just was not enough. They needed an entirely new category of material. And this is where the story changes, because PEEK wasn't discovered by accident. It was designed with intent. For the first time, polymer scientists approached materials the way mechanical engineers approach structures, starting at the molecular level. They asked better questions. What kind of molecular backbone resists heat? What kind of bond survives aggressive chemicals? How do you add rigidity without making a material brittle? And how do you keep it processable so it can actually be formed and shaped and molded and manufactured in different ways? And just like we say here at Vision Miner, the quality of your questions determines the quality of your outcomes. The answer wasn't a single feature, it was a balance. PEEK uses a rigid backbone made of aromatic rings, essentially stiff ring-shaped structures that act like structural beams, giving the material heat resistance and strength. Ether links act like flexible joints in that structure, allowing controlled movement so the material doesn't shatter or become unworkable. Ketone groups add chemical stability, helping the polymer resist fuels and acids and steam and harsh industrial environments. It's not too stiff, it's not too soft, it's not too fragile. What emerged was something fundamentally different. A polymer that didn't just tolerate extreme environments, it was built for them. And that polymer was PEEK, Polyether Ether Ketone. And this is exactly why, for nearly the last decade, we've built our entire platform around printing materials like this. Our 22IDEX high-temperature 3D printer was designed specifically to handle polymers that behave like PEEK, materials that don't forgive shortcuts, but reward proper thermal control and process discipline. So once PEEK existed, entire design constraints disappeared. Metal replacement became realistic, not theoretical. Weight could drop without sacrificing reliability. Components could survive heat and chemicals and stress simultaneously. In aerospace, parts got lighter without compromising safety. In medicine, implants or tools could be sterilized repeatedly and still behave predictably. In chemical processing, components stopped dissolving, swelling, or corroding under all these acids and chemicals. PEEK didn't replace everything, but it replaced materials where failure was no longer acceptable. And that's why it quietly became one of the most important engineering polymers in the world. Now, PEEK wasn't created to look impressive on a data sheet. It was created because metals and conventional plastics could not solve the problems that modern engineering demanded, and everything about its structure reflects that intent. At Vision Miner, this is the material world that we live in every day, designing machines and processes and workflows specifically around high-temperature polymers like PEEK. If you want the deep technical breakdown, how the molecular structure works and why PEEK has outperformed other high-temperature polymers, how it's actually processed and 3D printed in the real world, that's where we're going next. If you have specific questions, leave them in the comments below, but definitely subscribe and like. We've got a lot more videos like this coming to you. And of course, if you want 3D printers, 3D scanners, or help with any of those things, give us a call or shoot us an email. Anyway, thanks for watching. Have a positive rest of your day, and I'll see you on the next video.